Bismillahirrahmanirrahim. We will continue our discussion on virtual memory and discuss further more techniques in virtual memory management. In previous lecture, we were discussing page replacement algorithms. So we will continue page replacement algorithms in this lecture too and see what other page replacement algorithms have to say. Next algorithm is least recently used. What does least recently used has to say? This algorithm states to replace a page that has not been used in recent past. Optimal page replacement algorithm focused on future, and this least recently used algorithm focuses on past. Again, the example shown uses same string that we have used in both previous page replacement algorithms in order to make comparison among them in terms of page faults. 4 frame size is shown in this example, and you can apply it on any frame size given to you. So here you can see page number 1 is loaded in frame number 1. Page number 2 is in frame number 2. Page number 3 is in frame number 3. And page number 4 is in frame number 4. Next required page is page number 1, which is already present, so there is no page replacement. Since page number 1 is already present in frame number 1, as you can see, so there is no page fault. Next required page is page number 2, and it is already also present in frame number 2. Next requirement is page number 5. Since page number 5 is not present, so we have to first create space for it. So according to this algorithm, we have to focus on past. So a look back is created here of size of frame size. Since 4 frame size is used in this example, so 4 pages look back is created. The page that is farthest away in past will be the one that will be swapped out. So we can see page number 2 is used in recent past. We cannot replace it. Page number 1 is further away, so we cannot replace it. Page number 4 is little more away, while the farthest away is page number 3. So page number 3 is the one that is used least in past. So we can replace page number 3 with frame number 5. Next requirement is page number 1 again, and page number 1 is already present, so there is no page fault. Next requirement is page number 2, which is also present here, so there is again no page fault. Next requirement is page number 3. Since page number 3 has already been swapped out, so we have to brought it in again. What we have to do is make a look back of 4 frame size. So 4 pages look back is created. So now compare the pages in the frames and the pages in this look back. The one which is far away will be replaced. As you can see, page number 2 is extensively used in past, so we cannot replace it. Next, farthest, so page number 2 cannot be replaced as it is used too much in past. Page number 1 is also used in recent past, so we cannot replace it. So page number 5 is also recently brought in. So only odd one out is page number 4, which is not present in the look back. So we can replace page number 4 with page number 3, as you can see here. Next required page is page number 4. Again, as we have swapped out page number 4, so page number 4 is required again. So what we have to do is to create a look back. We have to create a look back of 4 pages. So let's develop a look back. Starting from page number 3, the look back is this: 3, 2, 1 and 5, and compare the pages in the frames with the pages in this look back. We have the frame structure as this. This is the frame structure. So page number 3 has been recently used in past, so we cannot replace it. Page number 2 is also used recently in past. Page number 1 is little away. Page number 5 is the farthest away page used in past. So the option we are left with is to replace the page that is used least in recent past. So page number 5 is the one that is used least in recent past. So page number 5 goes out and page number 4 comes in at its place. Next required page is page number 5, and we have the look back as page number 4, 3, 2 and 1. So making comparisons with the pages in frames and the pages in this look back, we would find the odd one out. The page structure, frame structure is this one. This is the frame structure. So page number 4 is used recently in past, we cannot replace it. Page number 3 is little far away in past, so we cannot replace it. Page number 2 is further little far away, we cannot replace it. And the farthest away in past is page number 1. So page number 1 is used least in past, it goes out and page number 5 comes in at its place. Hence this algorithm goes to completion. For our understanding, we maintained a look back, but in the system, a counter is implemented with every page table entry. Whenever a page is referenced, the counter is set, and hence it counts the number of times a page has been referenced. The one having least value in counter will be replaced. That means it has been used least in the past. So total number of page faults in this case are 4. As you can see, 4 page replacements have been made. Another example for least recently used is in front of you for your better understanding. As you can see, first 3 pages are loaded in the 3 frames here. So next reference page is page number 2. Since page number 2 is not already present. So we have to create space for it, and for this we have to make a look back. Since least recently used focuses on past, we have to make a look back and see which page is far away in past. One is most recent, so we cannot replace it. 0 is recent, we cannot replace it. So 7 is the one that is far away in past. So 7 goes out and 2 comes in. Next algorithm, next page to be brought in is page number 0. But as you can see, page number 0 is already present, so there is no page replacement. Next page to be brought in is page number 3. So you can see here page number 3 is the next page to be required, and this is the frame structure. So we create a look back and perform the comparison with the pages in frames. 0 is most recent, 2 is little far away, 1 is though very far away. So 1 is replaced with page number 3. Here you can see. Next reference is page number 0, and 0 is already present. Next reference is page number 4. So again, what we have to do is to make a look back. So look back of 3 frames is created here. That includes page number 0, 3 and 0. 0 is intensively used in past, so we cannot replace it. So, and 3 is also used in past, so the only option we are left is page number 2. So page number 2, which is not used in recent past, it goes out, and page number 4 comes at its place. Hence, the example goes on till the end. I hope you can complete it by the end of the string, applying least recently used on every next reference. I hope this must be clear to you now. Let's now move on to next algorithm, which is least frequently used. It is an approximation or substitute to least recently used that says replace a page that has least frequency of use or least intensively used in past. Again, it focuses on past. It is applied or used rarely, as here wrong page may be selected for replacement. The one which has just been brought in memory may be replaced as it has least frequency of use in past. So this selection may turn out wrong. Hence, this algorithm is rarely applied. Next algorithm is not used recently. It is based on the principle that the page which has not been used in recent past may not be required in near future. So such a page must be replaced by the incoming page. Additional information is added to every page table entry for this algorithm, which are addition of reference and modify bits. If a page is referenced, its bit is set to 1. Otherwise, the reference bit stays 0. And if it is modified, the modified bit is set to 1. Otherwise, remains 0. So the replacements are made by looking at these 2 bits. Next replacement algorithm is principle of optimality. It is based on prediction, and prediction is based on the use of a page. If a page will not be used again in future, so it gets replaced with the new coming page. But prediction for whole or demand of pages cannot be made perfectly. Hence, this algorithm is also used rarely. Another page replacement algorithm is random page replacement, and it states that all the pages in the memory have equal likelihood of being replaced. There is no criteria for selecting a process for replacement, as at random any page can be replaced, even the one which is required or needed next. Decision is made very quickly here. So again, this is not considered an effective algorithm. Hence, it is used very rarely. Next topic of discussion is address translation by direct and associative mapping. We are finished with the page replacement algorithm. So now we are coming towards the address translations. There are three mechanisms for address translation, and the first one we are going to discuss is the direct mapping. As already mentioned, this translation process in previous chapter. So here again the same procedure is represented in front of you. In direct mapping, direct translation from logical to physical address is done using page table. CPU generates a logical address. This is the logical address consisting of page number and offset. The page number is indexed with page table. Page number gets indexed with page table. To get the respective frame number, and the offset is then linked with this frame number in order to get the actual physical address of main memory. So here you can see the frame number is obtained from page table, and offset is added with it as it is. The corresponding physical address then is generated. This translation mechanism have already been discussed previously. Translation look-aside buffer is used to reduce the number of times main memory is accessed. Since the page table is also stored in main memory along with the process, so main memory is accessed twice. Once to access the page table and second time to access the required frame. In order to avoid this twice memory access problem, a special buffer or cache is maintained to store the page table entries. One buffer is maintained for all the page table entries that are most recently used of all the processes in memory. So with this buffer, the page table in main memory will not be accessed, and translation look-aside buffer will be first examined to locate the frame number, hence reducing the memory access to single attempt. How translation process works? Given the logical address, the processor first examines the translation look-aside buffer to get the frame number in order to access the physical address. If page table entry is found in translation look-aside buffer, that means translation or TLB hit is observed and frame number is fetched from there. Offset is linked to it and respective physical address is generated. But if the respective page table entry is not found in translation look-aside buffer, that would result in TLB miss. So the same old mechanism then will be used, that is to first get page table entry from main memory and then get the required frame from main memory, leading to again two main memory accesses. Translation look-aside buffer gets updated time to time in order to accommodate the latest pages, and older pages are deleted, replacing them with new ones. Here is the difference between direct and associative mapping. In associative mapping, the use of translation look-aside buffer is visible. You can figure out the difference between them. In direct mapping, the page table is located in main memory. So, first page table is accessed to get the frame number. And then, in order to get the actual physical address, this frame number is linked with offset. And again, main memory is accessed to get the required location. While in associative mapping, the translation look-aside buffer is maintained in form of a cache holding all recently used page table entries of different pages of different processes. Page table is first searched in translation look-aside buffer to fetch the respective frame number. And if it is found, this frame number is linked with the offset in order to get the physical address. So, only single access to main memory is made to get the actual location. Keep in mind that page table is maintained for every process, which means every process has its own respective page table. But translation look-aside buffer is maintained only one for all the processes. No process has its own translation look-aside buffer. Only single translation look-aside buffer serves all processes. Here is the diagram showing TLB hit and TLB miss in shape of combined direct and associative mapping. First, page number is searched in translation look-aside buffer. If TLB hit happens, frame number is fetched. From there, offset is connected to it to get the physical address. But if TLB miss happens, the page table is then accessed to get the frame number. And then offset is linked with it to access the actual physical address in main memory. It may happen that respective page is not available both in TLB and page table. That means the page is invalid. So then page fault occurs and the required page is first loaded to main memory from secondary storage, and its invalid bits is reset to 1 from 0. And then the translation procedure continues in similar fashion as discussed earlier. Last topic of discussion is pre-paging in this chapter. Pre-paging is a concept in which operating system in advance loads some of the pages to main memory in an attempt to reduce the page faults. The loaded pages are those which are not yet referenced. So this may overload main memory with useless pages. Hence, pre-paging may create problems for operating system in managing main memory. So pre-paging is considered an issue for operating system. That is it. This is the end of this chapter. I thank you all.